Welcome back to The Explainer. Today, we're taking a seriously deep dive to demystify the physical world and peel back those invisible layers of reality. You know, from the device you're holding in your hand right now to the most extreme, mind-bending phenomena in the cosmos, we are exploring the molecular architecture of matter. So let's just dive right in. We see an ice cube melt or water boiling into steam, and we barely give it a second thought, right? Or think about why you can smell a bottle of perfume from entirely across the room, or why a balloon expands. It is so easy to take these everyday occurrences for granted. We look at a rock and we just know it's hard. We feel a breeze and know air is invisible. But why? Well, the answers to these incredibly simple, foundational questions all lie in understanding the states of matter. And today, we're going to answer every single one of them by looking straight at the invisible building blocks of our reality. Here is how we're breaking it down for today's explainer. Number 1, matter versus energy. Number 2, the classic 3. Number 3, the cosmic state. 4 is the weird and exotic. And finally, number 5, why do states change? All right, kicking things off with section 1, matter versus energy, the absolute foundation of reality. So reality basically has a very clear dividing line. On one side, you have matter. Matter is anything that has mass and occupies space. It's the stuff you can literally touch, hold, or see. The water you drink, the wood of your desk, the screen you're looking at right now, heck, even the air in your lungs is matter. Energy, on the other hand, well, that has no mass. It doesn't take up space in that same way, and you can't usually see it directly. Energy is simply the ability to do work. Think heat, light, or electricity. So a great little memory trick here is matter equals mass plus space. And energy is just what makes that matter actually do something. Moving right along to section 2, the classic 3, solid, liquid, and gas. Now, to really get why a solid is solid and a gas is a gas, we have to talk about intermolecular forces. These are the attractive forces between molecules. Honestly, think of this as an invisible glue that dictates how absolutely everything around us takes its shape. See, matter is made of particles, and these particles are constantly moving. But how closely they're packed together and how much distance exists between them, that is entirely controlled by the strength of this invisible molecular glue. I love this analogy. Imagine the particles in matter as a bunch of kids playing on a playground. In a solid, those kids are holding hands really tightly, just locked together. In a liquid, they're still holding hands, sure, but much more loosely. They can kind of shuffle and slide around each other. But in a gas, those kids aren't holding hands at all. They're just running totally wild, freely all over the playground. Keep that image in your head because it makes these next 3 states make total sense. First up, the solid state. A solid has a fixed shape and a fixed volume, and that's entirely because of those extremely strong intermolecular forces. The particles are holding onto each other so tightly that they're packed closely together, kind of like bricks in a rigid, sturdy wall. Because they are packed in so densely, they can't move freely at all. They basically just vibrate in place. This is exactly why a rock, or a piece of iron, or a block of ice holds its shape and is practically impossible to compress. The structural integrity is just totally locked in. But in the liquid state, the rules kind of loosen up a bit. A liquid has a fixed volume. Like a liter of water is always going to be a liter of water. But it doesn't have a fixed shape. Those intermolecular forces we talked about, here they're only moderately strong. The particles stay close, but they have just enough freedom to slide right past one another. This looser molecular bond allows liquids like milk or oil or water to adapt perfectly. You pour a glass of water into a tall, thin bottle or a wide, shallow bowl, and those particles just slide around to perfectly take the shape of whatever container you put them in. And then we reach the gaseous state. Here, those kids on the playground, they completely let go. Gases have absolutely no fixed shape and no fixed volume. The intermolecular forces are incredibly weak, which means the particles are super far apart and moving rapidly, totally free in every direction. And because of all that empty space between the particles, gases are highly compressible. Remember that question we asked earlier? This chaotic, rapid movement perfectly explains why the smell of perfume spreads so incredibly fast across a room. The gas particles are just zooming freely through the air. Let's step it up a notch. Section 3, the cosmic state, introducing plasma. Welcome to the 4th state of matter. Plasma is essentially a gas that has been energized so intensely, heated to just mind-bogglingly high temperatures, that the atoms literally tear apart. It becomes this wild soup of freely roaming electrons and positively charged ions. Now, you can actually find this ionized gas right here on Earth, if you know where to look.
It's inside fluorescent tube lights, it's in the glowing arcs of a welding torch, and it's definitely in the blinding flash of a lightning bolt. But honestly, its true home is on a scale much, much bigger.
Seriously, check out this mind-blowing statistic. 99% of the visible universe is made of plasma. Our sun? That's just a giant ball of plasma. Every single star you see in the night sky? Plasma. Those three classic states we just spent all our time discussing, the solids, the liquids, and the gases that make up literally everything you have ever known or touched, they make up a measly 1% of the visible universe. So these earthbound states that we consider normal are actually an incredibly rare anomaly in the grand scheme of the cosmos. Crazy, right? So, synthesizing everything we've covered so far, you can see a really clear logical progression. We start from a solid with a fixed shape, fixed volume, very small distance between particles, and high density. Then we step down to a liquid, which loses its fixed shape but keeps its volume. Down to a gas, losing both shape and volume as the distance between particles gets large. And finally, all the way out to plasma, where the atomic structure breaks down entirely, creating vast distances between charged particles and incredibly low density. It's just a brilliant progression of the energy scale of matter. All right, let's get a little crazy. Section 4, the weird and exotic, bending the rules of reality. Let's kick this off with supercritical fluids. Under some very specific extreme conditions of temperature and pressure, the boundary between a liquid and a gas just completely disappears. You get this substance that flows and expands like a gas, but, and here's the kicker, it acts as a solvent and can dissolve materials exactly like a liquid. A prime example is supercritical carbon dioxide. And this isn't just some lab theory, it's incredibly useful stuff. We use this bizarre hybrid state every day to do things like safely decaffeinate coffee, manufacture complex medicines, and even clean super delicate electronics without leaving a single trace of residue. Next up, we have liquid crystals. This is another one of those fascinating intermediate states. A liquid crystal physically flows like a liquid, yet if you zoom in on a microscopic level, its particles maintain a highly rigid, structured arrangement just like a solid. And look, if you think this sounds super abstract or theoretical, I absolutely guarantee you are looking at it right now. Liquid crystals literally power the LCD, liquid crystal display, screens on your television, your computer monitor, and the mobile phone sitting in your pocket. Now, consider graphene. This stuff is a real game changer. It is a single, isolated layer of carbon atoms, perfectly arranged in this beautiful hexagonal honeycomb pattern. It is literally exactly one atom thick. One atom. Yet, despite being unbelievably light and completely flexible, it is a phenomenal conductor of heat and electricity. But honestly, here's the most astonishing fact. This one atom thick material is roughly 200 times stronger than steel. It is literally revolutionizing how we manufacture everything from flexible touchscreens and solar cells to super advanced medical devices. And man, the universe just gets weirder from there. Scientists are continuously studying exotic states of matter that don't naturally exist anywhere on Earth. Take the Bose-Einstein condensate, for example, which only occurs near absolute zero, literally the coldest possible temperature in the universe. At that freezing edge, individual atoms just stop behaving individually, and they merge together to act as one giant superatom. Or how about dark matter, the invisible, mysterious mass that's quite literally shaping entire galaxies? There's nuclear matter, crushed under immense gravity inside neutron stars. And quantum spin liquids, this highly special magnetic state where electron spins are locked in a constant chaotic dance. The universe is just unimaginably vast and wildly complex. So, bringing it all back home, Section 5, why do states change? The cycle of energy. How exactly do you go from one of these states to another? Well, it's all about energy, specifically the simple addition or removal of heat energy. When you add heat to a solid, the particles gain energy, and they start vibrating faster and faster until they overcome those strong intermolecular bonds, melting right into a liquid. Add even more heat, they gain even more energy, eventually breaking free entirely through evaporation to become a gas. But if you reverse the whole process, remove that heat, the particles lose energy and they slow down. The gas undergoes condensation back into a liquid, and the liquid undergoes freezing back into a solid. The amount of energy dictates the strength of those bonds, and that directly dictates the state. Simple as that. As we wrap up today's explainer, I want you to consider this thought. Matter is the building block of everything in the universe. Chemistry helps us understand the world, from the smallest particles to the vast universe. Just by understanding how particles arrange themselves, how they hold hands, and how they react to energy, we literally unlock the mechanics of our reality. We learn exactly why an ice cube melts in our glass, why water flows down a river, why lightning glows in the sky, and how advanced materials like graphene are going to build our future. So, take a quick look around the room you're sitting in right now. Which invisible forces shaping the matter around you will you notice today? Are you going to look at the steam rising from your coffee, or the glass of your window, or maybe even the glow of your screen with a newfound awestruck scientific lens? The architecture of the universe is absolutely everywhere, just waiting to be understood. Thank you so much for joining me on this deep dive into the states of matter. Keep questioning, keep observing, and I'll catch you in the next explainer.